Hi guys, so today we're starting chapter 4, which is our big unit on polynomials and polynomial functions. So today is just going to be an introduction to polynomial functions. We are going to talk a little bit about some terminology or vocabulary for polynomials, something called the degree, their end behavior, roots or zeros, which we've already referenced beforehand, and then multiplicity of those roots and how to sketch polynomials. So quite a few things today. All right, so for the warm-up, you are just finding the roots or the zeros of these functions, very similarly to how we did this when we were talking about finding roots or zeros of quadratics. In a lot of cases, the roots or the zeros are also the x-intercepts, not always, so that's why we have this different name or a different vocabulary for them, is in case they don't actually cross the x-axis if they're imaginary. So what I want you to do is pause the video, go ahead and set the functions equal to 0, and then you can use factoring to try to find the roots here, okay? And once you've done this and worked it out, then go ahead and unpause the video and you can double check that your work looks correct. So I'm gonna go ahead and show you my work on the second page here. So for number 1, I set f of t equal to 0 to find the zeros, okay? And then I look to see, okay, I actually have a GCF here. 1/2 multiplies into both of those terms. So if you factor the GCF out in front, you are left with t to the power of 4 minus 1. And that is actually a difference of squares, which is a special case of factoring. So if you remember, we take the square root of the first term, so square root of t to the power 4, becomes t squared, and that's the first term in each parentheses. And then we take the square root of the second term, which is 1, and the square root of 1 gives us just 1. So we write that in the second spot in the parentheses, and then one of the parentheses has a plus sign and one of them has a minus sign. So that is how you factor the difference of squares, okay? Now the 1/2, that is technically just a stretch factor out in front. It's a constant, so if you wanted to, you could just divide both sides by 1/2, or you can just jump to splitting this up to where you take t squared plus 1, set that equal to 0, and t squared minus 1, and set that equal to 0, and solve both of them. So you're going to get 4 solutions here. T equals plus or minus I, because when you take the square root of the -1, it becomes I, and then t equals plus or minus positive 1. So here, it didn't explicitly say it in the warm-up, but here the implication is that we are only talking about our real roots, because the plus or minus I, those are imaginary roots since that has the imaginary number. So if we're just writing our real roots, so real numbers, we have 1, 0 and -1, 0. And we want to write those as coordinate points because we plugged in 0 for y, or for the function first and foremost. Okay, then number 2, we start out the same way. We set f of x equal to 0. I would then use grouping on this, so group the first 2 parentheses and the second 2 parentheses. Then you look here for your GCF. Okay, so in the first parentheses, you can factor out an x squared right here. In the second parentheses, you can factor out a -25 from both terms. And then we are left with those multiplying times x minus 4. Since those match here, that's perfect. We've done it correctly. So we get x minus 4 is multiplying times the x squared minus 25. That, again, is a difference of 2 perfect squares. So take the square root of x squared, which becomes x. Take the square root of 25, which becomes the 5. One has a plus sign and one has a minus sign. So now we have all 3 of our factors. We split them up using zero product property. We set them each equal to 0, and we solve for x. So here we would add 4 to both sides. Here we subtracted 5 from both sides. Here we added 5 to both sides. So our roots are at 4, 0, -5, 0, and positive 5, 0. Those are the 3 roots right there. So hopefully this is a little bit of a refresher. Again, we did this stuff in chapter 3. And the reason that we're putting this on the warm-up today is because you're going to do a ton this unit with finding the roots of polynomials. So this is going to be hopefully fresh in your brain. Okay, so first of all, let's define what is a polynomial. Polynomials are functions that you have seen a lot up until this point in math. Many of the functions we've worked with actually are polynomials, and you'll see on the next page I go through some of those common examples. So a polynomial function is often written in this format. This is what you would see in a college algebra textbook or something like that. And really the easier way to remember this is that a polynomial is a combination of, as you can see here, variables and numbers or terms being added together, where all of the exponents are only positive whole number exponents. Okay, that is not as important for our purposes because really for this chapter we're just going to be working with polynomials the whole time, but just so that you are aware. Okay, now one really key thing to know is what the degree of a polynomial is. So the degree of a polynomial is the highest power or the highest exponent. So if we look here, this would be the highest exponent, and oftentimes if we've written the polynomial in standard form where we have the highest exponent first, that's just the formal way of writing it, then this one will be out in front, okay, or we want it to always be out in front, and then we'd say it has whatever that degree is, degree n, okay? Then the term in front of this, so a sub n right here, that is just going to be some number that's multiplying times the variable, and that we call the leading coefficient, which you guys are already probably used to. We've talked about that before in other avenues. Okay, and then the term with that highest degree, that entire term together, so this a sub n times x to the power of n, that is just called the leading term because it's out in front, or it should be out in front. All right, so let's look at 4 examples of very common polynomials. So the first one, f of x equals 3, you notice there's no variable. This is not multiplying times x, and it's not to the power of anything. If we did write this times x to the power of something to make it equivalent, that'd have to be x to the power of 0, because x to the power of 0 or any number to the power of 0 is 1, except for 0. Okay, so this is a 0-degree polynomial. And we have a special name for this. This is called a constant function. This is the same thing as y equals 3. Okay, f of x and y, those are interchangeable, which is just a horizontal line like that. So 0 degree, that's always going to be a constant function. Okay, a horizontal line there. So then look at the next one. We've got our variable here, and the exponent that we don't see written there is actually a 1. So that's the highest exponent that we see attached to a variable, which is 1, and so that means that this is a first-degree polynomial. So first-degree polynomials we call lines. Those are linear functions, and they look, you know, something like that. You guys are super familiar with that. All right, the next one, we look at our variables. Which one has the highest exponent? Well, this one does. So this is a second-degree polynomial, which, if you recognize this, this is a quadratic. So quadratic functions are all second-degree polynomials. And we know that those look like that U-shape, the parabola. Okay, and then last but not least here, just for these examples, this one we look, where's the highest exponent? It happens to be out in front, but you always want to check and make sure it's not out of order. So this is a third-degree polynomial because of that 3, which we call a cubic function. And cubic functions typically look like this, you know, kind of backwards squiggly S shape. So again, these are just 4 of the most common polynomials you see is 0 degree, first degree, second degree, third degree, and then obviously you have all the higher degrees from there, 4th degree, 5th degree, etc. Okay, so let's quickly talk about domain and range of polynomials. So polynomial functions, just so you guys know, if they have a degree of 2 or higher, they are going to be smooth, continuous curves, meaning they only have round curves, okay, no sharp corners, and they're continuous, so there are no breaks in the graph. You can draw the entire graph without lifting up your pencil. So if you take a look at these ones, so second degree or higher, we've got a parabola here, smooth and continuous, cubic function here, smooth and continuous, okay? So that's just something to know about those. Then if we talk about the domain and range of them, the domain of a polynomial function is always going to be all real numbers. It's going to go forever and ever and ever to negative infinity on the left side and positive infinity on the right side. Because they're smooth, because they're continuous, there are no breaks in the graph, they're not going to stop left to right. So polynomials always have a domain of all real numbers. That means x can be anywhere in that interval of negative infinity to positive infinity, okay? The range is a little bit different. So if you have a range of an odd degree polynomial, which we'll talk about in a minute, but odd degree meaning first degree, third degree, fifth degree, seventh degree, any odd number, then the range is also going to be all real numbers. So y could also go forever and ever up to positive infinity and down to negative infinity, okay? The domain or the range of an even polynomial, even degree polynomial is a little bit different. Again, we'll talk about that shortly. Okay, so an odd degree polynomial, again, it's exactly what it sounds like. So if you have a first degree, third degree, fifth degree, seventh degree, etc., so any odd number, if that is the degree of the polynomial, it has a specific quality about it, okay? And so one of those things is that an odd degree polynomial always has its ends of the function point in opposite direction. So I want you to write that down. Ends of the function point in opposite directions. Ends of the function meaning when you look to the far left of a graph or the far right of a graph. Far left, far right, far left, far right, okay? So where does that point? Okay, so if you take a look at all three of these examples, you see here, let me just use a different color. One side of the function, the left side as it goes to the left, it is pointing down. And then as it goes to the right side of the function, it's pointing up. This one to the left side is pointing up. To the right side, it's falling. Here, to the left side, it's falling. To the right side, it's rising or pointing up. Okay, so odd degree is always going to be mismatched, meaning one side of the function points up and one side points down. So like so, or opposite, one side points down and one side points up. So they're always going to be pointing opposite direction. That's the ends of the function. Now, because of that fact, the other thing that you can note about odd degree polynomials is they're always going to have at least one x-intercept, so at least one real value of x that makes the function 0, or at least one real 0. Because if the ends are going to point in opposite directions and it's going to go to positive and negative infinity eventually, then it's going to have to cross the x-axis. Like here, it crosses 3 times, so you have 3 real zeros. We call those real just because, again, they're real numbers. They actually cross the x-axis there. They're not imaginary roots. Okay, here's one real 0. It crosses once. And then here, again, this one has 3 real zeros. So odd degrees are always going to have at least one real 0. All right, then even degree polynomials. So starting with second degree or fourth degree, sixth degree, eighth degree, 10th degree, etc. Okay, any even number. Now the ends of the function for an odd degree polynomial are going to point in the same direction. So the ends of the function point the same direction. Okay, looking here, you see these ends. So if you look to the far left of the function and the far right, they're both pointing upwards. And then same thing here. This, you look to the far left, it's pointing downwards or it's falling to the left, and then to the right, it is also falling, it's pointing downwards. So they're either both going to point upwards or the ends of the function are both going to point downwards. And just the names of these, even versus odd, can hopefully help you guys think of that. Even meaning the ends of the function, or if you look to the far left and to the right, they're evenly going to both point in the same direction, versus odd, they're pointing opposite. Odd, I always think, if this helps you guys, odd, I think opposite. Okay? All right, the other thing to note here is when it's an even degree polynomial, the range, like we talked about, is not going to be all real numbers, because there is going to be some stopping point, whether that is a minimum like this value, or if that is a maximum like this value. So it's always going to stop at one point, okay, and that means the range is going to look something like this. If if k, this value right here, is the lowest point or the highest point, then it's going to go from that value down to negative infinity, versus if it's the lowest point, it'll go from that value up to positive infinity, okay? And then the other thing to note is that even degree polynomials don't necessarily have a real zero or a real x-intercept like we see here, because they can be situated completely above or below the x-axis. For instance, you could have an even degree polynomial that looks like that, and it's completely above the x-axis and it's never going to cross it. Or you could have one that's completely below the x-axis and never crosses it either. So there's not a guarantee for even degree polynomials that it's going to have a real x-intercept or real zero. Okay, so I just mentioned a couple times the end behavior of these polynomials. So just the end behavior is what it sounds like. It's what the graph of the function does at its end. So when you look to the far left and to the far right of the graph. And we always read graphs like we read books. We read them left to right, okay? So the end behavior, you're just looking at both ends of the function. And yes, there are going to be some intervals on the polynomials where maybe it's increasing or decreasing and it goes up or down or up or down. But eventually, if you look to the far right, it's going to do something. It's going to have to go up or down. And then same thing with the far left. So eventually it will rise or fall without bound as it moves to the far left or right. And it will either rise to positive infinity or fall to negative infinity. So what helps us determine that is the leading coefficient and the degree n. Okay, and there's something that we use, it's called the leading coefficient test, and this helps us determine what the end behavior is actually going to do. Okay, so first of all, I didn't put this on a separate slide, but we have positive versus negative leading coefficients. And if we go way back to the very beginning, when we looked at the leading coefficient, that's just that very first term, okay, that's attached to the highest power. So whatever sign that is, that determines if it is positive or negative. So if it's positive, then as you go to the right, it's pointing upwards. If it is a negative leading coefficient, then as you go to the right of the function, it's pointing downwards. So kind of self-explanatory, okay? Positive, the end behavior to the far right is going to point up. So here, positive and positive pointing up. Versus negative leading coefficient is going to point down as you go to the far right, okay? And then once you determine if it is also even or odd, that's going to determine what the other end of the function does. So again, positive and negative, you see that as you go to the far right of the function. Okay, so now if I have an even function that's also positive, I know to the right it's going to point up. And if it's even, the other side is also going to point up. So you could have something like this, something like this. Okay, there are lots of different polynomials that are going to be even and positive like this, where both ends of the function point upwards. And you don't have to draw those examples necessarily. Okay, but one other thing you can write is as it goes to the right of the function, it is going to rise. And as it goes to the left of the function, it is also going to rise. So you could say rises. Oopsies, let me rewrite that. To the left and the right. Okay, even and negative. So we know the right side is going to point down because it's negative. Even, the left side is going to point the same direction to even it out. Okay, so this, we would say, the end behavior is that it falls, the graph falls, both to the left and right. And you're going to have some homework problems like this that ask you for a description of the end behavior. Okay, odd and positive. So positive, the right side of the function is going to point up, but odd, meaning the left side is going to point the opposite direction. Okay, so this one, if we look at what the left is doing, it falls to the left, but the right side of the function rises. Okay, so falls to the left and rises to the right. And then last but not least, odd and negative. So odd and negative. pointing down as you go to the far right of the function, and then odd, meaning the opposite side, the left side of the function is going to point up, opposite direction, okay? So this one rises to the left side of the function and falls to the right side of the function. So you could have something like this, something like that. Just to show you some examples here. Again, you do not have to draw all these. You'll see plenty of examples in the next couple of slides, okay? So that's what the leading coefficient test helps us to do. So let's take a look at this. It says use a leading coefficient test to determine the end behavior of this graph. So we look at our leading coefficient, we make sure it's in the correct order, and we have the highest exponent first, and then the rest of our exponents should be in descending order. So this one is in the correct order. We've got the highest exponent, the x to the power 4, that comes first. So if I look at this, okay, this is my leading term. So the degree would be 4th degree right here. And we know that 4th degree is an even number. So it's 4th degree and it's even. And then if we look at what's the coefficient, the leading coefficient in front of that, well, this is just technically a 1. And so that leading coefficient, which you can label LC, is a 1, which makes this a positive polynomial as well, okay? So it's 4th degree, which means it's even and it is positive. And we got all of that from looking at our leading coefficient and our leading term. So if I were to determine what the end behavior would be for this, because it's even and positive, I know positive points up to the right side of the function. Even means the other end of the function, the left side, is also going to point that same direction. So they're both going to rise, okay? Meaning, you could write this is that the polynomial rises to the left and right side of the function. And I also like to always just kind of draw my arrows here. That way I can visualize before I graph a polynomial or when I'm answering a question like this, what is actually happening to the ends of the function. And if you take a look here at this example, this confirms here that this is in fact positive to the right and to the left, and it's even, so it's rising in both spots. Okay. Other thing that we want to quickly talk about is turning points, or number of turning points of a polynomial. So this can be really helpful, especially when we graph polynomials, which we'll do momentarily. In general, if f is a polynomial function, okay, of the degree n, then the graph of that function has at most n minus 1 turning points. What that means is the maximum number of turning points it can have. So I'll just rewrite this in different words. Max number of turning points is 1 less than the degree. Okay, 1 less than the degree of that polynomial. For example, a first degree polynomial can have a max of 0 turning points. So what's 1 less than 1? Well, it's 0. So 0 turning points. Well, if you think about first degree polynomial, we said those are linear. Notice a line doesn't have any turning points. It's not changing direction at all. Versus a second degree polynomial, if we apply this same principle, it could have 1 less than 2, okay? So a max of 1 turning point. And if we think about secondary polynomials, those are parabolas, okay? They have 1 turning point, which is right here, the vertex, regardless of which way it opens. That is the place that it changes direction. So that's what we mean when we say a turning point. That is a point where the graph changes from increasing to decreasing or decreasing to increasing, okay? And also some of the ways that students can remember this, which is very informally, is like the hills or the valleys of the polynomial. Okay, meaning like where does it go down to where it looks like a valley or rise up to where it looks like a hill. So the maximum number of turning points it can have is 1 less than the degree of that polynomial. It can have less than that though. It doesn't have to have that maximum, that's just a maximum. So it could have that or less. Okay, so just using what we've learned about turning points and then the leading coefficient test and degree, let's go ahead and match each of these graphs with its function. So f of x, g of x, and k of x is what we've got here. First of all, let's just use the leading coefficient test to determine the degree of these polynomials, and then if they're even, odd, or negative, or positive, okay? So we look at this first one, f of x equals x to the power 4 plus blah, 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 blah. We make sure it's written in the correct order and that our highest exponent comes first, which it does. So this one is going to be a 4th degree polynomial because of this exponent. And since this is a positive 1 to the power, or 1 times x to the power 4, technically we don't see that 1, then it's also positive. So 4th degree is even, and we know that it's positive. And so positive means it's pointing up to the right side, and then even meaning the left side's going to point the same direction. So we've got that one, okay? Then let's take a look at the next one. So we've got a negative x to the power of 6. We make sure that that's the highest exponent it is. So this one is a 6th degree polynomial. 6 is an even number, so that's even. And we've got a negative 1 as our leading coefficient. So this is a negative orientation. Okay, so the right side is going to point downward since it's negative, and the left side is going to point the same direction because it's even. So we've got that one, and then last but not least here we've got our highest exponent first again, so this is a 7th degree polynomial here. We look to see, okay, well 7 is an odd number, so it's an odd degree, and there's a negative 1 as our leading coefficient again, so this is a negative facing polynomial, meaning the right side is going to face down. But since it is odd, the left side of the function is going to do the opposite, so it's going to rise. Okay, and then we look, obviously we're not paying attention to the other characteristics of the graph yet, which we'll need to do shortly, but we take a look at the graph and make sure that we can find matching ones here. So I'm looking for the first one, f of x, for one that rises both to the right and to the left, which would be only part C, or only graph C here. Okay, so this one represents f of x because we know that end behavior matches. That's the only one. All right, g of x is also even, but it's negative, so we are looking for a graph that points down for both sides of the function, both ends. So part A, okay, that would be g of x. And then k of x is going to rise to the left, fall to the right. So like so. Okay, so that significantly helps us determine graphs of polynomials is what is going on at the ends of the function as you look to the far left and the far right of what you can see on that graph. So end behavior is extremely, extremely important. And then the other thing we're going to talk about before we then put this all together in graph are finding the zeros of the polynomials. Now, this is very similar to our warm-up, and we're going to use a lot of the methods that we used in chapter 3 to find the zeros of these polynomials. So including factoring, sometimes including quadratic formula. As a reminder, zeros, which another word for this is roots, okay, zeros or the roots of polynomials, and then in many cases these are x-intercepts. So we use those words interchangeably. Okay, roots or zeros, you'll hear those most often. That is just where the function, the polynomial function, equals 0. Okay, that's where the zeros are. And so that's when we set f of x, the entire polynomial, equal to 0. We call them x-intercepts if they are real roots. So each real root of the polynomial is an x-intercept. And the reason that we move away from just saying x-intercepts this chapter and when we talk about polynomials is because oftentimes we will solve for the roots or the zeros of a polynomial and we don't get a real solution. We don't get a real number. but that doesn't mean those are not still solutions. They are, and so that's why we refer to them now as roots and zeros in addition to x-intercepts when they are actually real numbers. Okay, so let's just practice this once, I believe, and then, yep, we're going to move on to graphing after that. So find all the zeros of the polynomial, okay? We're going to set f of x equal to 0, and if you want to make a note of that, you can. So set f of x equal to 0, and then solve. That's all that we have to do to solve for the zeros. So I'm going to replace f of x with 0. I get x cubed plus 2x squared minus 4x minus 8. Now you'll notice this is a third degree polynomial here, so I cannot factor this using box and diamond. I would want to use grouping, and that is why we have used grouping up until this point, and really encourage you guys to start using that method of factoring, because when it comes to higher degree polynomials than just parabolas or quadratics, that's going to be super, super helpful. So I'm going to group the first two terms together and the second two terms together. I'm putting a plus sign in the middle just because I want to make sure I know that that's still all being added. Okay, then I'm going to look for a GCF here. So between x cubed and x squared, I can factor out an x squared. And over here between negative 4x and negative 8, I could factor out a negative 4. So I get 0 equals x squared times, this leaves me with just an x plus 2, and then I have the negative 4 that factors out in front times x plus 2 again. Okay, so x plus 2, that is our new GCF, and that is multiplying times these two terms, so times x squared minus 4. And then you have to make sure that this is completely factored, because in a lot of cases you'll factor it once and then it's actually factorable again. So x squared minus 4, that is a difference of two perfect squares, and you're going to see those a lot just like you did in our warm-up. So square root of x squared is x, square root of 4 is 2, and then one has a plus sign and one has a minus sign in between, okay? So make sure once you factored it once, you check all of your factors and see if you can factor it any further. Maybe using a different method, maybe using the same method again that you just used. So then we use zero product property. We split all of the factors up, set them equal to 0, and we solve. And now because you see the x plus 2 is appearing twice, you don't technically need to solve that twice, okay? It's okay to just do that once. So we get x equals negative 2 and 2, and again, because these are zeros and they're actually real roots, they're real zeros, so they cross the x-axis, which means they're x-intercepts, we're going to write them as points. So negative 2, 0, and 2, 0. Okay, so those are our roots. Now, what we would say here, in just a second, we'll apply this a little bit, but this at x equals negative 2, that technically, since it appears twice, we'd call that a double root, and again, I'll talk about that in just a minute. Okay, couple more things, and then we will jump to graphing and we'll be done with this lesson. The exact number of zeros in a polynomial is a pretty important thing. So whenever we have a polynomial with a certain degree n, that polynomial has exactly the same number of zeros. They may not be all distinct though. Distinct means, or distinct is another word for real. Okay, so they may not all be real number roots. They might be imaginary roots or complex roots, but it's going to have exactly the amount of zeros that matches its degree number, okay? Meaning a first degree polynomial is going to have 1 0 and only 1 0. A second degree polynomial is going to have 2 zeros and only 2 zeros. A third degree polynomial is going to have 3 zeros. And again, that's a combination of real zeros and then imaginary ones. So again, we call the real zeros, we call those distinct zeros or distinct roots. Okay, also, if you have a root or a factor that appears multiple times within a polynomial, just like we did here on the previous page, we had x plus 2 times x plus 2, which is the same thing as x plus 2 squared. Okay, if that appears multiple times or it has an exponent there attached to it and it's multiplying times itself not just once, then that is what we call the multiplicity. Okay, so that exponent attached to a factor for a polynomial is called the multiplicity, and should hopefully make sense because that tells you how many times does this factor multiply times itself. If you add up all of the multiplicities of the zeros, it should give you the same number. It should total up to give you n. Okay, and the multiplicities, those determine the shape of the graph. So I want you to write these down. This is very, very important. So if you have a 0 and it has an even multiplicity, so multiplicity of 2 or 4 or 6 or 8 or 10, etc., then that means it is going to touch the x-axis at that 0 or at that root, and it's going to turn back around. Okay, another way of saying this is it's going to bounce at that x-intercept. So if I were to draw just an example here, okay, it's going to come down to that value r, and it's going to bounce back up and go the opposite direction, or come up and then touch it and bounce back down. Okay, so it's not going to cross straight through it. It's going to just go up, touch it, bounce back down, or vice versa. Okay, and that's actually why parabolas make the shape that they do, because they have a multiplicity of 2 a lot of times at those zeros that just touch the x-axis. Okay, if you have an odd multiplicity, so meaning, whoopsies, right here, meaning 1, 3, 5, etc. If you have an odd multiplicity, it actually crosses the x-axis instead of just touching it and turning back around. One thing to note that's not on the slide here is if it's a not first degree, if it is a multiplicity of 1, which I'm going to just abbreviate multiplicity of 1, it crosses straight through that root. Okay, so it crosses straight through that x-intercept or that root. If it is an odd multiplicity but it's 3 or higher, then think about what the shape of a cubic function does at the x-axis most often. That is going to flatten out and make that S shape. Okay, so that shape at the x-axis flattens out / S shape. Okay, and I'll show you some examples shortly here. So that's what's going to happen at that 0. Okay. So let's take a look at this example. We're going to determine the zeros and the multiplicities of the polynomial and then describe what the multiplicity tells you about the behavior at each 0. So if we find the zeros here, a lot of times you guys can start to do this in your head if it is already in factored form for us like it is here. So instead of having to write this out and set f of x equal to 0 and then set each factor equal to 0 and then solve, you can just probably do this in your head. Okay, so we get the zeros of -5, +2, and -1. So 5, 0, 2, 0, -1, 0. Those are my 3 zeros here. Okay. However, we have to take a look at the multiplicity. So we said multiplicity is the exponent attached to that factor. So if I look here, x plus 5, I don't see an exponent. But since it's just here once, that's going to be an exponent of 1. So 5, 0 has a multiplicity of 1, which I'm going to write here, multiplicity of 1, which means, we just said on the previous page, it crosses straight through that x-intercept. Okay, it's going to cross straight through 5, 0. Then if we look at 2, 0, this has a multiplicity of 3. It's being multiplied times itself 3 times. So if we were to write that out, we'd have x minus 2 times x minus 2 times x minus 3. And a multiplicity of 3, or higher odd degree, or higher odd multiplicities, we said that that flattens out at that root. or at that 0. Okay, so at 2, 0, it's going to make this flattened out shape, which is honestly kind of the hardest to draw out of all these, but we'll practice it. And then -1, 0, this one has a multiplicity of 2, and that is going to bounce at -1, 0. Okay, now if we add all of these up together, since this is in factored form, if we add all of these multiplicities together, that should give us our degree. So 1 plus 3 plus 2, so 4 plus 2 is 6. So this is a 6th degree polynomial. Okay, if we add them up, which is even, and if you look at the leading coefficient out in front, it's just a +1, and so this would also be positive if we were needing to gather that information to then graph it. Okay, so this, again, this is a different form than standard form. It's not all being added together. It is multiplying this factor times this factor times this factor. So if it's in factored form like this, then the degree number, you can't just look at the highest exponent for. You have to add all of those exponents, all the multiplicities, because if we were to actually distribute and multiply this whole thing out after expanding, then we would get something with x to the power of 6 in it. Okay, phew, we've almost made it. This is a long one. So putting all of these parts and pieces together is what helps us to graph polynomials, which is actually really cool without even having to use a calculator. So these are the steps. I'm going to have them on the following 2 slides where we go through 2 graphing examples and then do your homework. So you can write them down now or later. The first step is we're going to determine the degree and end behavior, so use the leading coefficient test to determine what direction the ends are going to face and all of that. Then we find the zeros, their multiplicities, and the behavior like we just did. And then to get an extra point, we're going to find the y-intercept. Then once we have all that information, we can actually sketch the graph, and we call it a sketch just because we're not picking other specific points. So it's going to include the end behavior, the intercepts, and we can use symmetry and turning points to help us as well. And then last but not least, we can check the graph on Desmos or a graphing calculator. But I will say for this unit, even though you can check on a graphing calculator, it's really, really important that you are doing all of these steps here and writing them out beforehand, because we know you guys can use a calculator, and that's not what we want you to know. So I will be testing you on the ability to actually gather all of this information and graph from that rather than just using your graphing calculator. Okay? So let's go ahead and graph this polynomial. You can take a minute to write this down, and then I'm going to leave room on the next page actually so that I just don't run out of room here. So I write this out, and I want you guys to do the same thing on your homework. You will have to do these same types of problems. So we are going to determine the degree and end behavior, the zeros, the y-intercept, and then we will actually graph it. So looking at this first one, I have to add up the multiplicities here, the exponents here, because this is not written in standard form. It's in factored form. So this is an exponent of 2. This would be an exponent of 1. So if I add those together, that would give me 3. So this is going to be a 3rd degree polynomial. And then if I use a leading coefficient test, the leading coefficient out in front is a -2. So this is going to be a negative polynomial, okay? And 3rd degree I know is also odd. So 3rd degree odd and negative. And then I want you to go ahead and draw what the arrows of the end behavior are going to do. So negative means to the right, it's going to point down. And since it's odd, the left side of the function is going to point opposite direction, so up. Then let's find our zeros. So if we set, let me use a different color here. If we set f of x equal to 0, we get -2 times this whole thing. You could divide everything by -2 because that is just a constant out in front, and 0 divided by that is just 0. Okay, and then we can go ahead and split this up. X plus 2 equals 0 and x minus 3 equals 0. Now, technically, you can write the x plus 2 squared equals 0, but then when you square root both sides and you square root 0, you're just still going to get x plus 2. So that's why you don't have to write that multiplicity there. You can always just write what's inside of that factor, okay? So then we get x equals -2 and x equals 3. again, this is something that you guys can start to get a little bit faster at and probably do a lot of this in your head. So negative 2, 0, and 3, 0. And not only do we need to determine the zeros, but we also have to determine their multiplicity. So if I look back here, this one, negative 2, has a multiplicity of 2. So I write that. And then 3, 0 has a multiplicity of 1. So multiplicity of 2, we said it's going to bounce at that 0, and multiplicity of 1, it crosses straight through. And you do all of this, you write all of this out before you actually draw the graph. Okay, and then the y-intercept, we always just set x equal to 0. So f of 0. Okay, and then I'm going to have negative 2 times, plug it in here, 0 plus 2 squared times 0 minus 3, and then we just need to simplify. So 0 plus 2, if we simplify our parentheses, those come first, is just 2. 0 minus 3 is minus 3. Okay, then I have to do the exponent next, so 2 squared becomes 4, and then I can multiply. So negative 2 times 4 is negative 8, times negative 3 is positive 24. So our y-intercept is the point 0, 24. All right, so after you have done all of this, you've determined the end behavior, the degree, if it's even or odd, if it's positive or negative. By the way, positive or negative is also what we call the orientation. Just how is it oriented in space. After you've done that and you found the zeros and the y-intercept, then you can go ahead and graph it. And again, this is a rough sketch because we're not gathering other points aside from the x and the y-intercepts or any points that we get from symmetry. Okay, so first thing I do is I graph the zeros. So negative 2, 0 and 3, 0. And please make sure when you're graphing this, if you don't have graphing paper at home, that you are making these tally marks or these tick marks just to show me your scale on your x or y axis, okay? So those are there. And then 0, 24, that's going to be way, 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 way up here off of my graph, okay? So I know that that's going to go up really, really high, more like up here. All right, so I can't really graph that right now. What you could do instead is just make your axes a little bit tinier and closer together. All right, and then I look to see, okay, where are my arrows going to point to the far right and to the far left? So I know that the far right, we said, is going to point down, and the far left is going to point up. And I want you to draw those arrows in beforehand. You can always go back and erase them if you need to change it a little bit later on, but I want you to draw those because then you know where the ends of your function should be pointing. Okay, then at negative 2, 0, I need to look back at the multiplicity and see what it does. So negative 2, 0, it's got to touch it and bounces. So it bounces back up, and I know that's going to go way, way, way up here, 0, 24, wherever that is. And then it's got to come back down to go through 3, 0, and it crosses straight through. So it's going to cross straight through and then keep going down. Okay, so something like that. Again, this is a rough sketch, so we're not going to have all of the exact points, but this gives you a gist of it, which is awesome. Okay. Next example, and then we are going to do homework. So we've got f of x equals x cubed times x minus 3 times x plus 4 quantity squared. So looking at the degree, it's in factored form again, which oftentimes it's going to be, unless it's in standard form, then you're going to have to probably factor it to graph it. So I'm going to look at all these multiplicities or all the exponents and add them. Again, when you don't see one like here, you need to add it in. So 3 plus 1 is 4 plus 2 is 6. So this is a 6th degree. 6 is an even number. So 6th degree, even, and then I look at the leading coefficient. This is out in front just a positive 1, so this would be positive leading coefficient. So using this information, because I know it's positive, the right side of the function is going to point up. Even, meaning the left side is also going to rise or point up. Okay, then the zeros, I set f of x equal to 0. Okay, and then here, notice this x cubed, that is not a constant, that has a variable. So anytime it has a variable in it, you need to actually split that up. That is one of the zeros, and you set it equal to 0. So x cubed equals 0. Notice what happens again if you cube root both sides, that goes away and you just get x equals 0. So you could also just automatically look at that and say, oh, okay, x is going to equal 0. So x minus 3 equals 0, which means x equals 3. And then x plus 4, quantity squared equals 0. Again, if you square root both sides, you get just x plus 4 equals 0, so x equals negative 4. Okay, so here are your 3 zeros. So 0, 0, 3, 0, and negative 4, 0. We determine the multiplicities now, so look back to see what's the exponent. So 0, 0 has a multiplicity of 3. This one is going to make that flatten out S shape, so it flattens out is what we're going to say. 3, 0, that just has an exponent of 1, so it's a multiplicity of 1, which means it crosses straight through it. And then negative 4, 0, that has a multiplicity of 2, which means it's going to bounce. Okay. Then, last but not least, the y-intercept. We are going to plug in 0 for x. So we get 0 cubed times 0 minus 3 times 0 plus 4, all that squared. And then we are going to simplify. So 0 cubed is 0. 0 minus 3 is negative 3. 0 plus 4 is 4 squared. And then it doesn't matter what these give us. This is 16. 4 squared is 16 times negative 3 times 0. That just all equals 0. So my y-intercept here is just 0, 0. Okay, so now we're going to go ahead and graph this. Also, you can say, so for these multiplicities of 3 or higher, you can say that that crosses the x-axis. It does cross the x-axis too. So that's another word you can say it, but it's more likely to flatten out because it's multiplicity of 3. Okay, so 0, 0, 3, 0, negative 4, 0. I put my x-intercepts there. And then, or my real zeros here, I draw my end behavior, so the right side and the left side, both of those are going to rise. And then I look to see what is going to happen, what's the behavior at each 0. So at negative 4, 0, I look and I see this bounces. Okay, so it's got to touch it, go back up, and bounce. I know it's going to also have to go through 0, 0 again because, you know, that's our y-intercept here. So it'll have to turn around, come back to 0, 0. Somehow. So at 0, 0 now, this is going to flatten out. So it's going to go up somewhere and then it's going to come back down. And instead of just crossing straight through it, because it's at multiplicity of 3, it flattens out. And this is a little bit harder to draw. So I sometimes like to draw the flattening out beforehand. So it almost makes that little, again, squiggly S shape. Okay, so it's going to flatten out there. And then it's got to turn back around to come back through 3, 0, and that's just going to cross straight through. Again, we don't really know how far these turning points are going to go up or down. That's where it's just a sketch. And also, notice here the difference. This is crossing straight through versus this is flattening out right here. So that's the difference here between the multiplicity of 3 and that multiplicity of 1, is that, yes, they're both crossing through, but one of them crosses straight through and one of them flattens out. Okay, the other thing that we talked about earlier is turning points and checking those. So if this is a 6-degree polynomial, the max it's going to have is 5 turning points. And sometimes that helps students just to write that over to the side to make sure that they don't have more than that. So if you notice, here's one of them. This is where it changes from decreasing and increasing, etc. Here, here, here. Okay, so this does not have more than 5 turning points, so we're good. We didn't go over that number. We did not exceed it. Okay, Last but not least is when we think backwards about these types of problems. If you are given information about the zeros and the degree, can you come up with an equation for the polynomial? And the answer is yes. So oftentimes we are going to write it in factored form first, and then we are going to rewrite that in standard form if we need to. So this one says, find a polynomial with degree 3 that has zeros at -1, 2, and 3. So if we think about our zeros, they are always the opposite sign of what we start with up here because of the process of zero product property. So if we're working our way backwards, we could set it up to where we have y equals, or I'm going to write p of x, p standing for polynomial, equals, okay, we've got 3 zeros, so we're going to have 3 parentheses. We need the x out in front. That's going to come in front of our zeros. And then we switch the sign because it's the opposite of zero product property. So this would become a +1. This would become a -2. This would become a -3. And then if it said leave it in factored form, this would be good. Okay, we would check to make sure the degree matches. So is it third degree? Yes, because this is a multiplicity of 1, 2, 3. When we add all those together, they're each multiplicities of 1. So this would be in factored form. And then if we needed to rewrite this in standard form, we could just go ahead and distribute this out, multiply that whole thing, and then continue to multiply again. And multiply all of this together, okay, to get standard form, whatever that would give you. So just pay close attention to the directions on problems like that. Okay, writing a polynomial equation from a graph. This is very similar as this information. It's when you're given that information, but now it's in graphing form. So what you'd want to gather is information about the graph that's really, really important. So looking first of all at the zeros, okay, and writing those down. You've got -3, 0, 0, 0, and 2, 0. And then you'd want to note what the minimum multiplicity is. So you could have higher than the multiplicity you're thinking, but you'd want to write down the minimum. So this one crosses straight through. So you'd assume, okay, the minimum that's going to be is a multiplicity of 1. This one bounces, so the minimum multiplicity would be a 2. If it is a multiplicity of 4 or 6 or 8, it's also going to bounce though. So any higher even number could be that multiplicity. So that's why we say, again, the minimum. And this one crosses straight through, so it's at least a multiplicity of 1. So then if you work your way backwards, we would write out x plus 3 right here, opposite sign, x minus 0, or just x, and that one would be squared at least, okay, because it's a multiplicity of 2 or higher even, and then x minus 2, and that's also a multiplicity of 1, we're assuming. And if we look for which one is correct or which one matches that, that would be part B. Okay. Phew, we finally made it. This one, like I said, is a long lesson, but all really important information. So go ahead and write down your homework for today. You've got homework from these 3 different pages. I know it looks like a lot, but I think it's only 12 or 13 problems total. And a lot of these you're going to be practicing writing out all of the information we just did. So degree, leading coefficient, even or odd, positive or negative, y-intercept, zeros, and then graphing.